So today we are going to do a problem on graph algorithms. So this is the question: roads and libraries. So the question is telling. I will tell the summary. I hope that you read the question. You can read the question from here. So the question telling is there are some cities in the hackerland, and we want to build a library that the cost is minimum so that everyone can also everyone can access the library. Cost should be minimum, and everyone can access the library. That means there should be a road to every member in city to come to the library. So here is the most important theory part behind this algorithm. Let's think that the there are 1, 2, 3, 4 nodes. No matter how I draw the graph, the minimum edges that I needed from I started from one node, I want to go to every node in my graph. The minimum number of nodes I need, minimum number of roads I need is n minus 1. N is the number of nodes in the graph. That the important is if there is some two nodes that are disconnected from this graph, that they should not be included. Okay. If they are in the same, it's a connected one, not kind of disconnected one. If they are connected from n minus 1 minimum steps that we can go to start with some node and go to any node. For this example, if we started from node 4, let's say, okay, we want to build some roads, okay. We build 1, 2, 3. From these three roads, from every node we can go this node. Every node can come to this node. Okay. Okay. So we can make this edge too, but that is unnecessary. The minimum is n minus 1. You can do any kind of. Okay. If I do something like this, I start 4, and from 4 I can go to any of others. So this is the theory, the first theory that I want to tell. So the cost is equal to the, if we say, let's say we make one library. So one library plus n minus 1 times the road cost. So that is the cost for one connected graph. Okay, disconnected graph, it is kind of a different situation. So let's consider this. So let's take that example. There is 1, 2, 3, 4, and minimum number of 3 is needed to go to from 1 to go to any of these. Minimum of 3 roads are enough. Let's say if we make two libraries, what will happen? Let's say here we make a library and here also we make a library. So the cost is now 2 times the library plus, let's imagine for the generality, if I make a new library, the k cities can go to that library easily. So the other library is n minus k cities. Okay. K nodes can visit the new library. So total number is n. N minus k nodes can visit the previous library. So if we consider this part, so k minus 1 paths are there, paths needed times 0 plus n minus k means what? N minus k means other nodes. So k nodes are connected to this new library. Since the n is the total cities, n minus k are still there. They go to the previously built one. So n minus k minus 1 time roads are enough. So I should multiply it by road. So if you simplify this, it is C library I will label times C road. It is k minus 1 plus n minus k minus 1 C road. So the k is cancelling. So if you simplify this, C is library plus let's say n minus 1 CR plus there is another C library here minus C road in here. So if the cost of a library is greater than the cost of the road is greater, you can see this becomes positive. So surely the cost becomes higher than if we are only build one library. So you can clearly see it there. Okay. If we build more libraries, if libraries price is greater, it is always okay. This is we consider the most general case. It is always become more expensive. But if what happen, C library is less than the value of C library is less than the value of C road, this becomes negative. So cost become low. So in that kind of situation, every time we make a library, the cost become low. So what should we do is, if the cost of the library is low, we should, if we make every library in the every city, the cost is low. Because you can clearly say, I consider the two case, if another library is made, another this kind of a term is added to there, this same term added to here. So it will also become minus minus, so the cost is again low. So every time you make a library, cost become low. But if library is greater, there's no point of making even two libraries, because it was always become expensive. So the problem is asking the minimal cost. So our plan is, first, if library price is less than, no matter what the conditions are, we should make all the libraries in all the cities. So that is the first theory. And the second condition is, if roads are more cheaper, what should we do? So if roads are more cheaper, our equation is, cost equation is C library plus n minus 1 times C road. But this n minus 1 is for, that in our example, that connected one. So if there exists some kind of disconnected one, then other distinct library should be here as well. So we should calculate cost for this and for this. Oh, sorry. Okay. This is the equation we want to prove if the road cost is more low. In this equation, what we are considering is one connected graph. Okay. I don't know, the connected graph is a defined term. What I mean is this. from starting, you start from another node, you can go to every node there. So in the problem, there is some kind of given that possible roads. Okay. So we should calculate cost for this graph and for this graph separately and add them. So our plan is to make a decision to find this, because this is given, this is given. We want to find this in a one particular graph. How many nodes are there that they are connected? If we were able to find those connected one, we can plug it to here and find a cost. Then we move to next one. If there is some other distinct one, we should find distinctly how many ends are here. And there is n is 2, here is n is 4, maybe there is also something called n equal 3. So how depth first search and breadth first search come here? If we do a depth first search to this one, do we need these two nodes? No, because when we are doing depth first search or breadth first search, what we are considering is this listing particular graph. So here is where we need GFS and DFS. By using GFS and DFS here, we can find the number of nodes connected to each other. That's the point. We can find number of points, nodes connected to each other using DFS and DFS. Here you do a breadth search or depth first search and find how many nodes are connected to each other. It's only two nodes connected to each other. Here there are four. So now let's do the program part. In previous, I explained the depth search and breadth search and implement the code. So I directly using the code here, and at that stage I explain the I will use depth search. Okay, in a future question we will use depth search. Here using both is okay. In the depth first search, I implement it using iterative approach, and here I use an recursive, because you know that in a recursion in iterative approach, to make depth first search, what data structure we use mainly is stack. If we think about the recursion is also when we are calling function and return is some value, it calling the function again, and the it store the value in a stack. So it is possible that you can define a depth first search like this depth first search recursive approach. It is nothing but same. You can think about it. It is the same as we derived earlier using a recursive approach. So let's get started. So directly what we can say is if C if the price of a library is low, cost of library is C lib is less than or equal to the C rot, we can delete to return, since there is should be return a long value it's given, we should return a long n times long n times C library. So yeah, we just find. So if the condition is satisfying, always making a library motif. So else what is happening? Oh, if you think about it, else is not needed, because in this if this condition is satisfied, it will always return the function, so else is not required. So what we now have to do is, the if you read the question, it is given the just the input as like this, okay, like this. So here they given as 1 2 are connected, 3 1 can be connected, 2 3 can be connected. The function that we already created uh, before is needed the adjacency list. So we should make our adjacency list. Adjacency list, what we have is, we have one node and what are the connected to it. So it is a nested vector. So inside the nested vector is zero element. How many nodes are connected to it? So now let's make adjacency list for the given inputs. So I should initialize nested vector. The values should be integers, let's say, because when your summation it can be long, but the values inside can be most of the time it's integer. So addition, and how many are inside it? It's n plus 1. And uh, then we should loop through our input for teacher I equal 0, I less than integer. We should find the size of the cities. So the cities is a nested vector given cities dot size, and I'm going to return the value, and I should be incremented. So we gather all the values in the cities, and here I take the variables. No, before, yeah, I can make variables like u is equal to the, since this is coming like nested vector, the first value, city's value in the ith one and the zeroth is u. I will explain how this happens according that v is equal to cities same I value but 1. So what is happening here is, let me go to the let me go to the not here, not here. What it just gave is, sorry, what it just gave is 1, 2 can be connected, and 2 can be connected to 3, and 1 can be connected to 3. So this, like this way graph is what they are giving. Like this way input is giving. But what we need is, for 1 it connected to 2 and 3. 2 it is connected to 1 and 3. 3 is connected to 1 and uh, is connected to 1 and 2. So in the loop, we first get this value 1, 2, this value. Here you can see here we get that value. Cities I means we get the first value here. Actually, we know that there is only two values. So this is, we make it as u. Let me put the bottom of the screen. Okay. So here you can see I0 means 1 is u value, and here is 2 is the v value. And then what should we do is the created list. Now we created the list now, adjacency. In adjacency, the u value should be what? It's v. The u value should be v. So we should push back v. And since this is a bidirectional one, we can also say that the weak element is push back u. So this is nothing but just we making the adjacency list. So if you think about this, if you make this as an example, in our adjacency matrix, 0, 1. Okay, so we go to the 1, this is u. So to this position, we pushing back the. Okay, so again you loop through 2 and 3 here, this value and this value 1 and 3. When you are looping through 1 and 3, you again get u and v. So again for u value is 1, that means here you push the value 3. So now you can see how the adjacency matrix is making this with these u and v values. We make some value. So adjacency it is the making. So yeah, after making now we have adjacency list. Now what should we do? Now what should we do is we should do a depth first search. We should do depth first search. But here in the depth first search function, you can see that we have something which should to track of they are visited or not. We should have a bool with visited values. So, so before that, we should create that visited one. We should vector bool visited with n plus 1 and as well as oh, for so all are false, all not visited ones. To track of the sum, I could make a variable s. So now let's do. Now I am adding a for loop through the visited one to get a better idea of what are visited, to track of what are visited and what are not visited. 0, 1, because there is nothing called 0. You can hear the cities again as 1 to some number. So that is why we always created the visited vector and the adjacency vector is n plus 1 things. We don't start with 0. So I is equal 1 to I is equal less than I is less than what? N, n, and the and the s is less than 1, and I should increment the and if this is the more thing, if this is not visited, the icon is not visited, what we should we do is we should do the depth first search. So depth first search. A depth first search. So I directly copy and paste this here because I already explained how the depth first search is working. Copy and paste it here. Paste it here. So the function name is depth first search recursion. It is nothing but just do the depth first searching. Here. Here, sir. So our function name is depth first search recursion. So I call it here depth first search recursion. So what is happening is since here we are passed by reference to visited value. So when we are passed by reference value, if there is some different kind of islands of graphs, that means two different graphs, our main intention is that if we know how many nodes in a one graph, one distinct graph, connected graph, we can easily count. Our main idea is to how many distinct graphs, and from each distinct graph how many nodes are there. So by doing a depth first search, we can find how many connected nodes in a particular uh, graph. Connected nodes. Okay, here we can find it. But to keep track of how many connected things are there, I do a difference. What is, whenever I make visited a node, I keep track of it. Whenever I visited a node here, I keep track of it. So I made a count is equal to 0. Whenever I visited something, I make it increment. Okay. Whenever I visited, I make it increment. So in the recursion also, so c is equal to c plus this one. So this is not a void actually. Now this is an integer function. I return the c value. So in here, in which c, we can tell that how many nodes in that connected graph. So here, we are calling the function in c. The c is derived to c. That is another function. We do test for search, and what we are is a starting node, adjacency matrix, adjacency list, and visited function. So since we passed by reference, you understand that no matter how much time we call this depth search recursive, they already visited and already visited. So they should not be include this counter. So we can count how many distinct nodes in that connected graph. How many nodes in that connected graph. So this is it. So after we call in the function, we increment the summation. We have sum, so it's equal plus 1 C library plus our equation. We have how many nodes in that particular distinct connected graph. So it's just C minus 1 times C 0, oh sorry, times C 0 0. So after this for loop, we should return the sum value. Okay. So we can go ahead and try this. Oh, shit. There is some kind of wrong answer here. Expected output. debug output, your output, etc. Oh, sorry guys, I get the problem here when I copy paste in the function. I have a here. Okay, so let's try again in a DFS because that's again seems that we have some kind of error here. Let's check again. Oh, okay. When I initializing the SCA, it should be s equal to 0 because there is no initial value then. Okay, I'm just adding the values here. There is no initial value, so it is just put some random value. I guess that is why we get that big number. Now we will yeah, we find that bug also. There are some small bugs here. Let us check. I guess this is a problem because in the visitor there is totally I think this should be equal to and if not that could be a problem. Yeah, fine. So that is it. So the summary is what we have done is this. The summary is this. We have proved that if the library is less than the rod, always make the library. If the rod is less than the library, find distinct nodes in a connected connected graph. I don't know this connected graph. I mean is they are connected like this, not isolated graphs like this. And plug into that equation we derived and find the answer. So that's for today. We'll meet in another problem.